All right, so we're going to go over worksheet 83 real quick. Make sure to be checking your work to see kind of what you got right, what you got wrong, and let's get right into it. So at this point, we should hopefully be able to recognize what is and what isn't a perfect square. The blockets that we did yesterday, those were obviously all perfect squares. And you guys did really well with that. So hopefully we were able to recognize that, hey, 36 is a perfect square, 100 is a perfect square. If I have a fraction inside a square root, the best thing I can do is break it into two separate square roots and solve them independently, right? The square root of 36, well, that's just 6. The square root of 100 is 10. And I want to make sure I've got a plus or minus in front, because it could have also been negative 6 and it could have also been negative 10. Now, this word here is what's going to get a lot of you on the test. I'm just saying that, putting it out there right now. Simplify completely, right? 6 over 10 is not completely simplified. I can divide the top and the bottom by 2, leaving me with plus or minus 3 over 5. That's completely simplified. All right? With number B, or letter B, I guess, because of that negative sign in front, that's going to override the plus or minus. The square root of 25 is just 5. Throw that minus sign in front. Boom. Nice and easy. Now, 24 is not a perfect square. If I don't have a perfect square, my brain should immediately start a factor tree. For 24, we could say 6 times 4, 2 times 3, and 2 times 2. So the square root of 24 I could rewrite as 2 times 2 times 2 times 3. I'm looking for pairs on the inside of my square root that I can circle up and bring out in front. When those twos come out in front, they fuse together into a single 2. And whatever's left over inside the square root stays inside the square root. I just got to re-multiply them back together. Plus or minus 2 root 6 is my answer there. Same thing with 48. Not a perfect square, very close to 49, but not quite. So I'm going to factor tree my 48. That's what we end up with. 2 times 2 times 2 times 2 times 3. Pair of 2's with a pair of 2's. Those are both going to come out in front. These make one single 2. These make another single 2. And I'm going to multiply them together, right? The 3 is all alone. There is no pair. I got to leave them inside the square root. Then 2 times 2 in front gives me plus or minus 4 root 3, right? Square root of 200, not a perfect square. So let's make a factor tree. 200 is just obviously 2 times 100. 100 is 10 times 10. Now this is the shortcut that we've talked about before. I don't need to keep going here because I have a pair of 10s with a 2 left over. The 10s are going to come out. The 2 is going to stay behind. Plus or minus 10 root 2 is my answer. If we did keep going, I would have got 2 and 5, 2 and 5. I would have had a pair of 2's and a pair of 5's. When I bring both those pairs out, just like we saw over here, we have to multiply them. And 2 times 5 would just give me 10 anyway, right? So when I'm doing a factor tree and I spot a perfect square, I don't really need to continue with that one. Over here, I knew that a 2 was going to pop out because of that 4. Same thing over there, my perfect square of 4. I know a 2 is going to pop out. But with that one, because we had multiple 2's coming out, as well with this one, we do want to keep going all the way. So it never hurts to extend your factor tree all the way. But some of us, are going to be able to, I don't know why I said that twice. Some of us are going to be able to recognize those patterns and make our life easier. And finally, the square root of 321. It should be a perfect square. That is 18 times 18. So my answer is just plus or minus 18. Right? Wait, that's not right. 18 times 18 is 324. 321. So this one, 321, I don't know why I put this one on there. It might honestly be a typo. I think it's supposed to be 324. But if I have a weird number like this is a good little teaching moment here. If I have a weird number like this, we've talked about this. The best thing I can do is try my best to divide it by a small factor. So dividing this by 2 won't work because it's odd. If I were to divide it by 3, I would get 3 times 107. Now, 107, I believe, is not divisible, but let me check. Yeah, 107 is a prime number, so I can't split this up anymore. My answer is just 321. No plus or minus sign in front because I didn't bring anything out. Now that, again, is simplifying square roots. If I'm estimating a square root, that means I'm just taking an educated, I wouldn't even call it a guess, making an educated conclusion about what one of these square roots might equal, and basically where it falls between. So the square root of 104, a little bit more than the square root of 100, a little bit less than the square root of 121, right? If I was looking at a number line, it would go 100, something, 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 104, something, 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 121. So it's going to fall somewhere in between these two nice perfect squares. Well, the square root of 100 is 10, and the square root of 121 is 11. So the square root of 104 is somewhere between 10 and 11. It's not between 100 and 121, because I'm talking about finding the square root. Same thing with 55. This is a little bit more than 49, a little bit lower than 64. So the square root of 55 must be between 7 and 8. 231, just over 225, not quite up to 256. So this is between 15 and 16. Our perfect square charts are going to be super useful when estimating the square roots, so make sure you have that glued into your notebook before our test on Monday, all right? Number 3, nice and easy, no math involved really. I just got to identify whether or not the numbers are rational. So remember, a rational number is defined as any number that can be written as a fraction of 2 integers. And an integer is any number that we see up on our number line. So the square root of 45 is not a perfect square. Immediately when I have the square root of a non-perfect square number, I know that this is irrational. If I were to plug this into a calculator, I would get a number that's real ugly, just like C. And when I have a real ugly decimal that's not repeating in any recognizable pattern, 2, 5, 4, 6, 5, 8, 7, 4. I have no idea what the next number is going to be after that 4. That is also an irrational number. But don't let the square roots fool you. Just because there's a square rooted number doesn't automatically make it irrational. Because if I can simplify it like here, the square root of 9 is just 3. So the negative square root of 9 is negative 3. Well, that is definitely a rational number. I can write it as the fraction of 2 numbers, negative 3 over 1. That's the fraction of 2 integers. That is a rational number. It's also an integer, but we'll get to that later. Number 4, solve the equations. This is just like what we were doing up top in number 1, but this time instead of being an expression that we're simplifying, it's an equation that we are solving. So we have to think about it like any other equation we're solving. What am I doing to x? Well, I'm squaring it. What's the inverse of squaring something? And that is taking the square root. So if I take the square root of both sides, the square root of x squared is x times x. 169 is 13 times 13. Pair of x's comes out. Pair of 13's come out. Nothing's left behind. X is equal to 13. But again, I could have said that 169 is negative 13 times negative 13. I wouldn't be wrong. So I need a plus or minus sign in front of my 13. That's what it means when it says both solutions. A positive 13 solution and a negative 13 solution. If you remember, we talked about I don't need a plus or minus sign in front of my x because x can already be anything, positive or negative. Same thing over here, square root both sides. The square root of b squared is b. Square root of 64 is plus or minus 8. Square root both sides, and I get c is equal to 15. Oh, sorry, plus or minus 15. So when you're taking the square root of both sides, you definitely have to include your plus or minus sign because you want to make sure both solutions are accounted for there. All right. Now, in the distance formula, I've got 2 points. I want to label them first and then plug them in. What does my distance formula look like? Well, it's d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So it's like a 4-piece puzzle where I'm plugging 4 numbers in as a substitute for these 4 variables. 1, 5 is my first point. I'll call it x1, y1. 7, 8 is my second point. I'll call it x2, y2. Right? Every point has an x and a y. The x obviously comes before the y, just like in the alphabet. First point, second point, boom, boom, boom. So now we're going to plug it in. I'm going to rewrite my equation. Have a good day, Mr. Brown. I'm going to rewrite my equation without the variables, and I'm just going to plug in my pieces. So x2 goes first. That's going to be 7 minus x1, which is 1. My next little parentheses here, y2 minus y1 is 8 minus 5. Now I'm just going to go through and solve this following PEMDAS. The P in PEMDAS is parentheses. 7 minus 1 is 6. 8 minus 5 is 3. The E in PEMDAS is exponents, so 6 squared is 36. 3 squared is 9. When I add these together, I get 45. Well, 45 is not a perfect square, but I can simplify it with a factor tree. 45 is 9 times 5. 9 is 3 times 3. I've got a pair of 3's that comes out. I've got a single 5 left over. 3 root 5 units is my answer. Remember, when I'm doing the distance formula, I want units on the end because I'm finding an actual physical length or a physical distance. I do not want a plus or minus in front because distance can't be negative. All right, distance cannot be negative, so there's no need to include the possibility of it being a negative number. For the second one, same idea. I'm going to label them the exact same. x1, y1, x2, y2. D is equal to the square root of 11 minus 7 squared plus 1 minus negative 2 squared. Now we've got to be really careful when we're plugging in a negative number here, because if I have 2 negative signs right next to each other, well, those are going to make a big old plus sign. 11 minus 7 is 4. 1 plus 2 is 3. Gives me 16 plus 9, which is 25. Square root of 25 is just 5 units. So a couple options, or a couple, possibilities for our distance formula here. It could be a nice perfect square. It comes out as a whole number. Or it could be a not so perfect square that I need to simplify with a factor tree. All right. There's the front side. Not too bad. Let's flip over to the back. This is what we just learned. Do these side lengths form a right triangle? I'm going to use the converse of the Pythagorean theorem, which tells me to take the Pythagorean theorem, a squared plus b squared equals c squared, and plug the longest length in for c. 8 squared plus 9 squared equals my longest side of 10 squared. 6 squared plus 8 squared equals my longest side of 10 squared. Now I'm going to solve this out, see if it's true or false. 64 plus 81 equals 100. That's definitely not going to work. That gives me something way more than 100. So this is not a right triangle. Number 6, 6 squared is 36, 8 squared is 64, 10 squared is 100. This does add up to 100. So this is a right triangle? You just write yes or no, but I wanted to clarify. This is a right triangle versus this is not a right triangle. Sorry I'm yawning so much. I'm exhausted, as I'm sure you all are as well. Number 7, we're going to use the Pythagorean theorem to find the missing side length. This is nice because it tells me that I don't know what C is. So if I plug 2 in for A, 6 in for B, and now I'm going to have to solve for C. It's nice and simple, quick, easy setup. 2 squared is 4. 6 squared is 36. Add those together and I get 40. Right? I'm going to try and get C all by itself by square rooting both sides. I got to do a factor tree for 40. That's 4 times 10, 2 times 5, 2 times 2. Pair of 2's comes out in front. 2 times 5 left over inside the square root. Units on my answer. Again, triangles, Pythagorean theorem, we're talking about length. So I don't want a plus or minus sign in front, but I do want units on the end. Same thing over here with B. I'm going to plug in nothing for A, 4 for B, and 5 for C. A squared equals 16, A squared plus 16 equals 25. Now if I want to get A all by itself, I got to move that 16 over to the right. How can I do that? If I want to move 16, I've got to do the opposite. I'm going to subtract 16 from both sides, leaving me with A squared equals 9. So when I take the square root, I end up with just A equals 3 units. Nice perfect square comes out to a whole number 3. No need to make a factor tree because I know my perfect square is like the back of my hand. Make it nice and quick. All right. Number 8 says, find the length of the hypotenuse for the following right triangle. For me to do that, I'm going to count my vertical distances. My vertical and my horizontal distances. Here, I've got 1, 2, 3, 4. 1, 2, 3, 4, 5. And my hypotenuse, I'm just going to call C. Well, if A squared plus B squared equals C squared, then 4 squared plus 5 squared equals C squared. So 16 plus 25 equals C squared. Add those together and I get 41. Now that doesn't mean my C side is 41 units. It just means that I need to do my last step, square root both sides, and I end up with C is equal to root 41 units because I can't factor 41. 41 is a prime number, so I can't make a factor tree. I can't break it up. All right, another way we could have done it is by taking the coordinates here and doing the distance formula to find this length, but that's more work than it needs to be. I'm not going to do that. Last but not least, finally, our Pythagorean theorem with pictures. So this tells me that I need to figure out where my hypotenuse is, right? If I look at this little square, again, it's always pointing right at the hypotenuse, which is C. So I'm going to plug in 4 for A, I'm going to plug in 8 for B, and I'm going to plug in C for C. It could be X, it doesn't matter. X or C is fine. 4 squared is 16. 8 squared is 64. Add those together and I get 80. Square root both sides. Leads me into a factor tree. Now 80 is 8 times 10. 8 is 4 times 2. 10 is 5 times 2. And 4 is 2 times 2. So I've got a pair of 2's, a pair of 2's, and a 5 left over. I'm going to rewrite this so we can see what I'm talking about. Here's my factorization of 80. So I got 2 pairs of 2's that come out. I'm going to multiply them in the front to get 4. 5 still left over in the square root. And this time I'm not going to say inches, I'm not going to say units, I'm going to say inches because that's the units given to me in my diagram. So if we don't have units, we can just say units. Otherwise, we want to make sure we're being specific. All right? Over here, my little right angle is pointing to 6, so that's my C. So now I'm going to have to solve for C. X squared plus 4 squared equals 6 squared. I could say X, I could say A, it doesn't really matter. A squared plus 16 equals 36, and this time I'm going to subtract 16 from both sides, giving me 20. If I do a factor tree for 20, I get 2 times 2 times 5. So when I square root both sides, the 2's come out, the 5's stay behind. Kilometers slapped on the end for my image. Or from my image, I should say. And finally, C, my little square is pointing at, again, 12 is my C. A squared plus 10 squared equals 12 squared. A squared plus 100 equals 144. Subtract 100 from both sides to give me 44. And then I'll square root both sides. 4 times 11, 2 times 2. Pair of 2's comes out, 11. It looks like a smiley face. Pair of 2's comes out, 11 gets left behind. Meters is my units. There's my answer. All right. Hopefully that helps. If there's anything in particular that didn't quite make sense, either go back to the lesson it's from and watch those notes again, or review some of your worksheets from this unit and see how it goes. All right.